Iniciar grabación. Hi everybody and welcome to this EB training workshop on EB Biogeochemical Modeling products. My name is Àlvaro de Pascual and I am developer of multi-year products in the EBMFC. In this practical session, we are using EB Biogeochemical Modeling products to visualize the coastal upwelling processes in the Northwest African coast. The EB domain covers the North Atlantic eastern coast, therefore it covers one of the world's biggest eastern coast upwelling ecosystems, the system known as the Canary Current Upwelling System. In the present exercise, we are going to learn how to visualize maps of surface chlorophyll concentration from the analysis and the reanalysis modeling systems. We also will compare the results of both products to see the different features of each system, and at the end of this tutorial we will learn how to visualize the vertical variability of chlorophyll by plotting a Hofmöller diagram of chlorophyll concentration in a specific location. This example is written in a Jupyter notebook that runs in a server, so that you don't need to install anything, you just have to use your web browser to access a web page. First of all, in the web page you will see some notes with instructions to run each cell code. To execute a code cell, we just select a cell and then push this triangle button at the top of the page, or additionally we can use the keyboard shortcut, the Shift Enter keys. This example is written in Python 3. So, the code cells are these cells with gray background. To run this cell, you just have to click on the cell, select the cell, and after that you have to push this run button. When the run has finished, here appears the number of the order sent to the server. In the table of contents, you can see the different sections we are covering with this tutorial. First of all, we have an introduction where we give a short explanation of the upwelling processes. After that, we put our hands on a section dedicated to produce different visualizations of the upwelling with EB Biogeochemical products. In section 2 is dedicated to produce multi-map of chlorophyll from the EB reanalysis. Section 3 is quite similar to the previous one, but it's dedicated to produce maps of chlorophyll in daily basis from the EB analysis system. And we will finish this tutorial in section 4, where we will learn to plot Hofmöller diagrams of chlorophyll. Well, let's jump into the introduction. The coastal upwelling processes occur in coasts where the wind blows parallel to the shore and the induced Ekman transport deflects the surface waters towards the open ocean. Then the mass balances forces the ascending of intermediate waters that are typically denser, cooler, and richer in nutrients. The high concentration of nutrients in upwelling ecosystem leads to the development of high primary productivity. Therefore, we can use the chlorophyll concentration as an indicator of the upwelling activity. In this example, we use the estimates of chlorophyll provided by EB Biogeochemical systems to see the different features of the upwelling in the Northwest African coast. In this example, we are using products for EB Biogeochemical modeling systems. However, since there is two different systems that can be used to visualize the upwelling, we will use both and then we will compare the results obtained. Here you have the list of the products of the systems we will use. The reanalysis system is focused in providing the best estimations for long-term periods, while the analysis products are focused on providing high-resolution estimates of the ocean routinely updated. However, the temporal coverage of this second product is not as long as in the case of the reanalysis product. As I said before, in this example, we are using the chlorophyll concentration that in the IBI Biogeochemical product has the name CHL. As usually happens with Python 3 programs, the first lines are devoted to load the necessary libraries that are used in the program. So the first code cell we have in the example is just a list of libraries used. Here you have a short explanation of the main purpose of each library, as well as the links to the reference pages. As we said before, to run this cell, we just have to select the cell and pass the run button here. With this, we can put our hands on and jump into the first exercise of this tutorial, the visualization of the upwelling of the chlorophyll, surface chlorophyll in moldy basis with IBI reanalysis products. First of all, we have a short section with a description of the data set we are going to use. You can download this data set from the Copernicus Marine catalog. However, this is the information you need to download this data set. However, we are not going to spend time on this. In this exercise, we already have all the data sets already downloaded. Here in this left panel, you can see a file browser with 3 different directories. In the directory data, you can see that we have 2 different NetCDF files. These files are the data sets we are going to use as data source. These NetCDF files are obtained from the Copernicus Marine catalog using this configuration in the subshelter interface. Well, in this case, in this in this exercise of the visualization of the reanalysis products, we are going to use this file, the reanalysis, the chlorophyll reanalysis in moldy basis. In the next exercise, we will use this other file, the chlorophyll from the system, the near real-time system, in daily basis. Well, we jump into the next section, which is the definition of the input data. Here we have the first cell for this program. In this cell, we specify some parameters that are going to be requested for the program we are going to write. There are some parameters like the file name we are going to use as data source. As you can see, it is one of the files stored in the data directory. Is the one provided by the reanalysis, the chlorophyll variable from the reanalysis in moldy basis. We also define some parameters to define the boundaries of the maps we are going to plot. We also have to define initial and end date because we are going to plot several figures, a figure for each time step in the file. And so we have to define when we want to start to plot figures, the date of the starting date and the finishing date. These dates are defined as datetime objects from Python 3. Finally, we also define a path out, a place where we are going to store our results. As you can see, this path is a directory of results, and inside results there is another directory, IBI Bio reanalysis moldy. So here we will have our results. Well, we can run this cell now. We can jump into the next cell, which is quite short but very important because it has the line that access the data in the source. To do that, we use the library xarray. And we use a function to open this file and create an object that is the object that we are going to use to access the data. Here we are printing this object, so we will the computer will return a short summary of the dataset we are open. Here you can see we are open a NetCDF file. As you probably know, the NetCDF files have three kinds of objects: the dimensions, the variables, and the attributes. In the dimensions, in this file, we have 4 dimensions: depth, latitude, longitude, and time. And here you have some numerical information of the dimensions. Depth goes from 0 meters, 0.5, up to 300 meters, latitude, longitude, and time. As you can see, time starts in 1992, January, and finishes in 2018, December. Here is the list of variables. You probably know that NetCDF files can store many variables, but in this case we just have downloaded one variable, which is the chlorophyll concentration. And here the list of main attributes of the file. This is quite general information of the procedure of the file. We can jump into the next, once the file is open, we can jump into the next cell. This cell is quite important because we are selecting the data we want to plot. To do that, we create a variable, we define a new variable that is a kind of shortcut to the selected data we want to plot. So the variable var points to the variable var name in the dataset, and we use the function cell to select specific values of each dimension. For example, we select a specific value of the depth, since we want to plot the surface chlorophyll. We are selecting the depth equals to 0, and after that we are modifying the variable var to select also other dimensions like latitude, longitude, and time. Since we are going to plot a sequence of maps, we have to select not just one value of the dimension, we have to select a range of values of each dimension. To do that, we use the function slice between the minimum and maximum value for latitude, longitude, and time. These lat min, lat max values, long min and long max values, and initial and finishing date are defined in the configuration cell at the beginning of the program here. So that at the end of this cell we print a variable var, so we will receive, as before, a short summary of the information we have stored in this variable. Here we have selected 17 time steps with 109 values of latitude and 133 values of longitude. And then we can jump into the next cell where we are plotting the maps. This cell is quite long because plotting the maps we have to define many variables. Here you will see that we define a for loop for every time value in the variable var. We create an object that is the time step, and we format this time step as a string to print this string. We can print this string, and then we create another variable selecting a part of the data stored in var. In this data to plot variable, we are selecting the specific time step we are trying to plot in this iteration of the loop, And from here we start to plot the data. To plot the data, we use the matplotlib library from Python. It's a very famous one. First of all, we have to create a figure, create the axis, and we use the function baseMap to create an object map. This object is an object where we are going to establish all the parameters that are requested to plot a map. For example, an important one is the projection of the map or the boundaries of the map. For example, here we include the latitude and longitude maximum and minimum in the map. After these lines, we have a few lines devoted to format, to give some formats to the plot. You can see we are adding to the map object few parameters. For example, we include in the map to drop the coastlines, to drop the country lines, to fill the continents. With this, we are creating a land mask in our map. We also say that in our map we will draw parallels and draw meridians. Particularly, we will draw 5 parallels and 5 meridians between lat max and lat min, and lon max and lon min. We also include in our figure the labels of the y and x labels, or y and x axis. And from here we are working with the data to create the grid and to plot the data. First of all, we have to create a grid. The data in the variable var are stored as a vector. This is, as you can see here, in latitude we have a sequence of values, but this is not an array with 2 dimensions. It's just an array with 1 dimension. It's a kind of vector with many elements. And in longitude it's the same. We have a vector with many elements, but it's not an array with 2 dimensions. We need to create our grid by transforming these vectors into arrays with 2 dimensions. To do that, we use the function meshGrid, very famous, from the library NumPy. And with this we create 2 variables that are 2 arrays with 2 dimensions. The longitude grid and the latitude grid. However, since we are plotting a map, we have to translate this latitude, longitude information into the format of x, y axis in the figure, in the plot. So we use the map object to transform this long lat information into x, y values. And to finish to plot this data, we use the function pcolorMesh from matplotlib, and we pass the following parameters x, y, and z, where x and y are the values of the grid, and z are the values we want to plot, the values obtained from the variable data to plot defined at the beginning of the iteration of this loop. It's worth to mention that in the definition of this plotting, we are including the information to do a normalization, a logarithmic normalization of the data between the mean value and the max value of the data, because, well, it's interesting in the case of chlorophyll. Maybe it's not as interesting in other scalar variables. We will see that later, the interest of using this normalization. Here we continue with our loop, including in the figure a color scale and a level for the color scale. We include in the figure also a title that it's a string that is formatted with this order. As you probably know, in Python 3 we can format strings with this order. Here we will replace this. The system will replace these brackets with the value of this variable. So the title of the figure will be IBI Bioreanalysis. Here we will put the variable name, and here this bracket will be replaced with the string date. Here we have to put this order to show the figure in the console, and also we finish the loop, the iteration, with saving the figure we are created. We also format the name of the figure using this command. This figure will be saved in the pass out that was previously defined in the configuration of the program in pass out. And we will use also the date of each figure to create a specific name of the figure. We will save the figure with format JPG, but we could use any other format. Well, we run this cell now, and here it is. We start to see the results of the maps of chlorophyll concentration. You see that the upwelling is clear here as a clear increase of the concentration of chlorophyll along the coast, the Northwest African coast. Here you can see that we start to see the files we are storing in this directory, you see. And since we are using a dataset with data on a monthly basis, we obtain a map for each time step. So we are obtaining a map for July 2015, July 2015, August, September, October, November, December, etc. You probably see that in July, in August, the activity of the upwelling, the concentration of chlorophyll along the African coast is much higher than during the autumn and winter months here. However, during the winter months, the upwelling is still present, so we can see an increase of the chlorophyll concentrations along the coast in the Northwest African coast. Here we are in February and March. Here we have the maximum of productivity in the spring, a typical process in the ocean. And here we see also the development of upwelling filaments. These kind of filaments are very well documented in the upwelling processes, and particularly the development of the filament in front of the Cape here and Cape Boucador here in the northwest coast of African continent is very well documented. Well, here we have all our maps, and we have a section of discussion of results where we propose to see the behavior of the upwelling. We have already done. How can we detect the upwelling? We have said there is the increasing of chlorophyll concentration along the African coast. Is it stronger, the upwelling, in summer or winter? Well, it's clear that it's clearly stronger during the summer months. And we have detected these filaments, for example, here in October 2016. We also propose some exercises. We are not spend much time in these exercises. However, we encourage all of you to try to do it, and if you have any problem, you can try to contact me and I will help you in any request you have. we propose to modify the previous code to show maps of focus on specific regions, and we propose to modify the previous cells to plot just one map of a specific date. Well, these two exercises are very simple. You just have to modify the configuration of the first code, of the first cell code. Here you can change the boundaries of the window you want to see in your plots, or you can modify the range of dates to be plotted. We also propose another exercise that I think it's very interesting. The maps shown use a logarithmic color scale. However, the differences observe the differences using a linear color scale. To do that, as you remember, I talked about this before. To do that, we have to change the line where we use the function pcolor-mes with the normalization, the logarithmic normalization, and we have to change this line for a line where we are not using such normalization. Here, for example, we have to go here. We can do this exercise very fast. Here, and as you can see, this line is commented with linear color scale and also with logarithmic color scales. We can change this line. In the logarithmic color scales, we have the normalization of the data. We request for the normalization of the data. We can comment this line and uncomment this line. And then we can run again this program, and let's see what happens then. Here you can see the results are not as clear as before, because it's the use of logarithmic color scales are clearly better for the plotting of chlorophyll concentrations. Right? The range of variability of chlorophyll is large enough to use a logarithmic color scale. Well, let's try to stop this and restart with logarithmic color scales. Okay. As I said before, here we have the files we have obtained it from the run of this cell. You can open these files and you see they are JPG files. You can open these files by double clicking them, and you will obtain the file to insert it in any document or whatever. With this, we finish this exercise, and we can jump into the next exercise, which is the visualization of the upwelling in daily basis with EBB or near real-time products. This exercise is pretty similar to the previous one, but we are using near real-time products, and we are using a dataset on a daily basis. So that we have a first description of the dataset we are using. As before, this dataset is already downloaded in the data directory. This is the dataset from the near real-time system with the variable chlorophyll analysis daily means. Well, as before, we encourage you to try to download this file using this configuration in the Copernicus Marine subsetter interface. And we can start with the example in the inputs section. As before, we have a first cell where we define the parameters we are going to need in our program. Many parameters are very similar to the previous section. for example, but there are some differences, like for example, the file name we are not using as before the reanalysis file. We are using the near real-time file for chlorophyll analysis in daily basis. The variable is the same than before. The limits of the boundaries of the maps are the same than before, but the range of dates we are going to plot are not the same. We are plotting from the month of July in 2020, from 1st of July up to the end of July. Since we have daily data, we will create 31 maps. And finally, we have a path out where we will store the results of these plots, of these 31 plots. As before, these results are stored in a directory inside the directory results in IBI near real-time daily here. Well, we run this cell code, and after that we can jump into this cell that is pretty similar to the previous one. In the previous case, we are opening the file name and creating a DS object, a dataset object. To do that, we use the library xarray, and we print the dataset. This dataset, we run the cell to get a short summary of the dataset we are open. Here you can see the properties of the file we have opened, and here we propose some discussion of the results. Please compare the summary with the one obtained in the EBF reanalysis data. Do you see any difference? To do that, we can split our window by clicking here, new view for the notebook, and we are having another view of the same notebook. So we can go to the section where we have received the report of the reanalysis, the report of the reanalysis file, and the report of the near real-time analysis file. Here we can look for the differences. You can see the variable is pretty the same, the CHL, the same name and same dimensions, time, depth, latitude, longitude, time, depth, latitude, longitude. But when we explore the dimensions of the file, we see that despite there are the same dimensions, the amount of the number of elements in each dimension is quite different. Here we have 433 elements and 541 elements, while in the reanalysis product we have just 145 and 181. This is because this file, the resolution of this system is much higher than in the case of the reanalysis. We also can see differences in the time dimension. If you see, in the case of the near real-time product, we have downloaded daily data from July 2020, the 1st of July 2020, up to the end of July 2020. While in the case of the reanalysis data, we have downloaded monthly data from 1992, January 1992, up to the end of 2018. Well, we can jump into, once we have checked the differences with the previous dataset, we can jump into the next cell code cell. This is a similar one to the previous exercise where we select the data to plot. We get the data from the variable var name in the dataset. We select the values nearest to the depth 0. And after that, we select inside the var, we select the latitudes, a range of latitudes between lat min and lat max, min, max, data init, date end. And we print the variable as before. We run the code and we obtain our report, sort of report, and we finally use the same code as done before to plot the maps. As before, we define a for loop over the time values in the variable var, and we do an iteration for every time step in the variable var, and we format the time step as a string, and we create a variable data to plot where we store the specific information of this time step, so that we select the specific information, select the element in the dimension time that is the same that time step. And from here we are plotting the map with matplotlib. We create a map, create a figure, create the axis, create a map. We draw coastlines, the boundaries of the borders of the countries. We fill continents. We draw parallels, draw meridians, exactly the same as before. And we also include the labels in Y and X axis. And as before, we have to create the grid, that long grid, with the mesh grid function from NumPy library. And also we have to translate this long last information into XY, into the axis of the figure. So we have to transform this lat long information in XY numbers for the axis of the figure. To do that, we use the map object, and we plot the maps with the function pcolorMesh from matplotlib. And as before, we are using the normalization of data, which is the logarithmic normalization between the mean value and the max value of the data. We add in the figure the color bar, the label of the color bar, title, as exactly the same as before. We show the figure and we save the figure with a formatted name. Well, we can run this cell code. And here we obtain the result of plotting daily values of chlorophyll concentration. Here you can see that it starts to appear the files we are saving in our system. And here you can see the evolution of the Upwelling system in July 2020. The high concentrations of chlorophyll near the coast are strongly related with the activity of the upwelling. Here, near to the southwest of Gran Canaria Islands, we can see one of the eddies produced at southwest of these islands. Is also a very famous feature process in these islands, produced by the dominant current here, the Canary current. And also we can see the evolution of the filaments of the upwelling during the month, and the evolution of some eddies near the filament. Well, let's jump into the discussion of results. See the influence of spatial resolution, comparing the maps obtained with the maps created in section 2. To do that, we are going to split again our window. New view for notebook. And let's go to the figures we have created from, for example, the reanalysis product in 2015, July. And this is an example. This is for the complete month, and this is for one day in this month in 2020, the same month. Well, we can observe the differences of the pixel size. They are clear that the pixel size here is much bigger than here, because the resolution of the reanalysis product is lower, it's clearly lower. And we can observe the differences in the oceanographic feature zones. As you can see, there is a lot of difference between these two maps. It's much blurred, the result obtained with this system, but this is not a result of different of the resolution. Is mostly produced by the fact that this map is just a monthly mean, while this map is just a daily mean. Right? So this map has the average of 31 elements. So the features are not as sharp as in the case of a daily mean. Well, do you think it's possible to plot the upwelling with the same time coverage and frequency than in previous step? Monthly means from 2015 to 2016 by using EBF near real-time data? The answer is not. That's not possible, because the near real-time data doesn't has in its time record results for 2015 or 2016. The near real-time system only has stored that data for the last 2 years. So now we are in 2020. This time period is outside of the record provided by the near real-time data. Do you think it's possible to plot the upwelling with the same time coverage and frequency? Daily means from 2020's July, 1st July up to the end of July of 2020, but using the system of the previous example, phi EB reanalysis data? Well, the answer is again not, because the reanalysis system is updated. It's updated in a delay mode. So we spent about 6 months or 1 year in updating the reanalysis. So currently we don't have information for the year 2020 in the reanalysis system. It will be created in a few months, but still we don't have this information. Well, again, we propose 2 exercises. We propose 2 exercises to modify the previous code to show maps focusing a specific region, and modify the previous cells to plot just one map of a specific date. You are free to try these exercises. I encourage you. They are not very difficult. You just have to change some parameters in the configuration of the program, and it's very easy to accomplish this. Well, with this we can jump into the last exercise of this tutorial, the creation of a Hofmöller diagram of chlorophyll. The objective of this exercise is to create a Hofmöller diagram with time in the x-axis and depth in the y-axis, and the colors will represent the chlorophyll concentration. Here we jump directly to the input section, because we are going to use a dataset already downloaded in a previous section, in the section 1. And we are using this data from chlorophyll reanalysis on a monthly basis, and it is stored in the data directory here as before, and we have to define a specific point of latitude and longitude for our plot and a maximum depth to plot. We define also a parameter, the path out, where we will store our results. Here we are going to produce just one figure, so we store our results directly in this directory. We can run this cell, and we jump into the next cell. That is a cell pretty similar. You will see things from previous exercises. For example, we are doing two things. The first one is to open the NetCDF file with the function from the XRI library as before, and we are creating the dataset object, and we print this dataset to obtain a quick look of the information of the dataset, and after that we are creating a fast map with a quick look of the selected location for our Hofmodel diagram. We can run this cell by pushing the run button, and we have our summary, and here we have a map with a red dot over the place we are going to produce our Hofmodel diagram. Well, after this cell code, we jump into a cell code very familiar for us now, which is a selection of data to plot. In this case, we create a variable var from the dataset, and the variable stored in dataset with var name, and we select the specific latitude and specific longitude with the nearest value. The method is the nearest value. These values, as before, are defined in the configuration of the program, and we modify also the variable by selecting the slice in depth, in the dimension depth. We select a range of values from 0, from the surface value, up to the max depth. Here we run this cell, and we obtain a short summary of the variable stored, and here we are creating the Hofmodel diagram. We use matplotlib again to create the figure, the axis. We put the background we set the background of the figure in gray color, and we use the function contour f as a function to create contour figures, contour plots. It's a function from the matplotlib library, and we pass to this function the following parameters: the x values, the y values, that are the time values in the x-axis, and the y values, the depth values in the y-axis, and the colors will be stored in the z dimension, which is the values stored in var. In this case, we have to transpose this array to make the same dimensions between x, y, and z. And here we are formatting the figure, including dates in the x-axis of the figures, and the x-axis includes some dates. And we are including the labels of the x and y axis. We invert the y-axis because the depth values are positive values, but they have to be plotted downward. And we include also a grid in the figure, a color bar, a label for the color bar. We include a title include a title in the figure, formatted as here, and we show the figure in the console, and we save the figure with a name, where, and store it in the pass out here. Okay, so we can run this figure, this cell, and here we have our model diagram of chlorophyll. You can see we can observe the annual variability of chlorophyll in the surface and in the first meters of the water column up to the 200 meters, which is what we have selected in the configuration program, in the configuration cell. We propose also an exercise to modify the previous code to include a limitation in the maximum depth shown in the plot. Well, you just have to modify the configuration cell of the program. This is all for this tutorial. Thanks for watching. I hope you enjoyed this tutorial, and I will see you in the next video. Thank you.